Welcome to Gravity Science. I'm really glad you're here tonight. Before we begin our journey, tell me, where in the world are you listening from? Maybe you're resting in a quiet room, traveling softly on a late night train, or wrapped in a warm blanket with your favorite drink. Wherever you are, I hope this moment feels peaceful, safe, and ready to carry your mind into gentle wonder. Tonight, you and I are going to take a journey together, a journey that stretches across time and space, across the smallest particles and the largest structures in existence, across the simplest moments and the most profound mysteries. We're going to explore everything, and I mean everything, from the quantum foam that bubbles beneath reality itself to the vast cosmic web that connects galaxies across billions of light years. But we're going to do it slowly, gently, with the kind of pace that lets your mind wander and your body settle deeper into rest with each passing moment. Let's begin right here, right now, with you. You're lying somewhere comfortable, I hope, feeling the weight of your body against whatever surface holds you. That weight you feel, that gentle pressure, is gravity at work, is the same force that keeps planets in orbit, that bends light around black holes, that shape the entire universe. And right now, it's cradling you, pulling you gently toward the earth beneath you, reminding you that you belong here, in this moment, in this place. Your body knows how to rest. It's been doing this since before you were born, since you were just a collection of cells dividing and multiplying in the warm darkness of the womb. Even then, gravity was there, shaping the way fluids moved around you, the way your mother's body oriented itself in space. Gravity is older than you, older than humanity, older than Earth itself. It's one of the fundamental forces that has existed since the very beginning of time, and it will continue long after everything we know has faded into the cosmic background. But let's not think about endings just yet. Let's think about beginnings. Let's go back, way back, to a time before time had much meaning at all. Imagine, if you can, a moment, roughly 13.8 billion years ago. There is no space yet, not in the way you understand it. There is no matter, no light, no structure. Everything that will ever exist is compressed into a point so small that our words fail to describe it. Smaller than an atom, smaller than a nucleus, smaller than anything we can measure or imagine. And in that infinitesimal point, there is all the energy that will ever be, waiting potential, about to become everything. Then, in a moment that we call the Big Bang, though it wasn't really a bang at all, and there was no sound, because sound needs air to travel through, and air didn't exist yet, the universe begins to expand. Not into something, because there is no something for it to expand into. Space itself is being created as it goes, unfurling like a flower opening in the morning, except in all directions at once, and those directions are being invented as they happen. In the first fractions of a second, fractions so small that we need scientific notation just to write them down, the universe goes through changes so rapid and so profound that everything we know is shaped by them. In the first billionth of a billionth of a billionth of a second, the four fundamental forces that govern all of reality begin to separate from each other. Gravity peels away first, the weakest of the forces, but the one with the longest reach, the one that will eventually build galaxies and stars and planets and you. Then the strong nuclear force separates, the force that will hold atomic nuclei together against the electromagnetic repulsion of protons. Then the weak nuclear force, the one responsible for certain kinds of radioactive decay. And finally, the electromagnetic force, the one that will let atoms bind together, that will create chemistry, that will allow complex structures like molecules and cells and brains to form. The universe is unimaginably hot at this point, so hot that matter as we know it cannot exist. There are only pure energy and the most fundamental particles, quarks and leptons, swimming in a plasma so dense and energetic that light cannot travel through it. Photons, the particles of light, are constantly being absorbed and re-emitted, scattered in every direction, trapped in this opaque soup of primordial stuff. But the universe is expanding, and as it expands, it cools. This is one of the most important principles in cosmology, one that echoes through billions of years of cosmic history. Expansion equals cooling. It's like when you let air out of a pressurized container and it feels cold against your skin. The universe is doing that, but on a scale that dwarfs anything we can create in a laboratory. After about 1 second, yes, one entire second has passed now, the universe has cooled enough for quarks to combine into protons and neutrons. These are the building blocks of atomic nuclei, the hearts of atoms. Protons are positively charged, neutrons have no charge at all, and together they will form every element in the periodic table, though not yet, not for a few more minutes. When the universe is about 3 minutes old, something remarkable happens. It's cool enough now, though still millions of degrees, for nuclear fusion to begin. Protons and neutrons start sticking together, forming the simplest atomic nuclei. Most of them pair up to make helium, the second lightest element. Some stay as single protons, which are just hydrogen nuclei, the lightest element. A tiny amount of lithium forms, the third lightest element, and that's it. That's all the nuclear fusion that happens in the early universe. Everything else, all the heavier elements, will have to wait. They'll be cooked later, in the hearts of stars, in a process that won't begin for millions of years yet. But even after nuclear fusion stops, the universe is still too hot for atoms to form. The nuclei are there, and electrons are zipping around everywhere. But every time an electron tries to settle into orbit around a nucleus, a high-energy photon comes along and knocks it loose again. The universe remains opaque, a glowing fog of charged particles and trapped light. You might want to adjust your position slightly now, finding a spot where your body can release just a little more tension. Maybe your shoulders can drop half an inch. Maybe your jaw can unclench. Maybe your tongue can rest more gently in your mouth. These small releases, these tiny surrenders to gravity, they're echoes of the way the universe itself learned to let go, to cool down, to allow structure to emerge from chaos. For hundreds of thousands of years, the universe continues to expand and cool, but not much changes on the surface. It's still this glowing, opaque plasma cooling degree by degree, waiting for a threshold to be crossed. And then, about 380,000 years after the Big Bang, the temperature drops below about 3,000 degrees Kelvin, and suddenly electrons can finally settle into stable orbits around nuclei. Atoms form. Hydrogen atoms, helium atoms, a trace of lithium atoms. The universe becomes electrically neutral, and in that moment, light is set free. All those photons that have been bouncing around for hundreds of millennia, trapped in the plasma, suddenly have nothing to scatter off of anymore. They begin to travel in straight lines, streaming through space in every direction. This is the cosmic microwave background radiation, and it's still traveling today. You can detect it with a radio antenna, a faint whisper of microwave energy coming from every direction at once, the oldest light in the universe, the afterglow of creation itself. By the time it reaches us, it's been stretched by the expansion of the universe, redshifted from visible light down into the microwave range, but it's still there, a message from the cosmic infancy, telling us about the conditions of the early universe. And in that newly transparent universe, where light can finally travel freely, there are tiny variations in density, places where matter is just slightly more concentrated than in other places. These variations are small, just 1 part in 100,000, but they're enough. Gravity begins to work on them, pulling matter from less dense regions toward more dense regions, amplifying the differences, creating structure. This is the beginning of cosmic architecture, the first sketches of the universe as we know it. The denser regions attract more matter, which makes them denser still, which attracts even more matter. It's a feedback loop, a gravitational crescendo that plays out over millions of years. Slowly, so slowly that you couldn't see it even if you watched for a human lifetime, the matter in the universe begins to clump. And there's something else at work here, something invisible, something that doesn't interact with light at all, but makes up most of the matter in the universe. We call it dark matter, though that's really just an admission of ignorance. We don't know what it is, we can't see it directly. But we can see its gravitational effects. We can see the way galaxies rotate too fast to be held together by their visible matter alone. We can see the way clusters of galaxies bend light from objects behind them, creating gravitational lenses that reveal far more mass than we can account for with stars and gas and dust. Dark matter is the scaffolding of the universe. It clumps first, creating gravitational wells. And ordinary matter, the stuff that makes up you and me and stars and planets, falls into those wells like water flowing downhill. The dark matter provides the structure, the framework, and ordinary matter fills it in, lights it up, makes it visible. Over tens of millions of years, the first structures begin to form. They're not galaxies yet, not really. They're more like proto-galaxies, clouds of gas falling into dark matter halos, heating up as they fall, beginning to swirl and rotate, and in the densest parts of these clouds, where the gas is compressed the most, where the temperature rises highest, something new is about to happen, something that will change the universe forever. Nuclear fusion is about to begin again, not in the universe as a whole this time, but in localized pockets, in the cores of the first stars. These stars are different from the sun, different from most stars you can see in the night sky. They're made purely of hydrogen and helium, with just a trace of lithium. There are no heavier elements yet, because heavier elements haven't been created yet. These are called population 3 stars, and they're massive, much more massive than the sun, burning hot and bright and fast. When one of these stars ignites, when the pressure and temperature in its core become high enough for hydrogen nuclei to overcome their electromagnetic repulsion and fuse together, releasing energy in the process, something beautiful happens. Light streams out from the star, and for the first time in cosmic history, there are points of light in the darkness, beacons shining across the void. The universe begins to light up, star by star, like a city coming to life at dusk. You might notice your breathing now, the way it flows in and out without effort, the way your chest rises and falls, in a rhythm as old as life itself. Oxygen flows into your lungs, crosses into your bloodstream, travels to every cell in your body where it helped convert nutrients into energy. That oxygen, every atom of it, was created inside a star. Not the first generation of stars, but later ones. Stars that were born and lived and died before the sun ever formed. The iron in your blood, the calcium in your bones, the carbon that forms the backbone of every organic molecule in your body, all of it was cooked in stellar furnaces, forged in nuclear fires, scattered into space when those stars died. You are made of stardust. That's not poetry. That's scientific fact. But we're getting ahead of ourselves. Let's go back to those first stars, burning bright in the early universe. They live fast and die young, these massive stars. A star like the sun will burn steadily for 10 billion years, but these first giants exhaust their fuel in just a few million years. And when they run out of hydrogen to fuse, they don't just fade away, they collapse. The core of the star, no longer supported by the outward pressure of fusion, succumbs to gravity and falls inward. The outer layers follow, accelerating, smashing into the core with such force that they bounce back in a cataclysmic explosion we call a supernova. For a brief moment, a single star can outshine an entire galaxy, and in the intense heat and pressure of that explosion, nuclear fusion goes wild, creating elements that could never form in the steady burn of a star's core. Gold, silver, uranium, platinum, all the heavy elements forged in the death throes of stars, scattered into space on the wings of supernovae. These explosions enrich the interstellar medium, the thin gas that fills the space between stars, with heavy elements, and the next generation of stars that forms from this gas will have those elements in them from the start. There'll be population 2 stars, still low in heavy elements, but not devoid of them. And some of those stars will have planets around them, rocky planets made of silicon and iron and nickel, planets with atmospheres, planets where chemistry can happen, where complexity can emerge. Our own solar system formed about 4.6 billion years ago from a cloud of gas and dust that had been enriched by previous generations of stars. The cloud was rotating slowly, and as it collapsed under its own gravity, it spun faster, like a figure skater pulling in their arms. Most of the mass fell to the center, where it heated up and eventually ignited to become the sun, but some of the material stayed in orbit, forming a disk around the young star. And in that disk, dust grains began to stick together. It started small, microscopic particles colliding and adhering, building up grain by grain. Then the grains became pebbles, and pebbles became boulders, and boulders became planetesimals, objects kilometers across with enough gravity to start pulling in material around them. These planetesimals collided with each other, sometimes shattering, sometimes merging, in a chaotic dance of destruction and creation that lasted millions of years. Eventually, a few planetesimals grew large enough to dominate their regions of the disk. They swept up most of the remaining material, becoming protoplanets. In the inner solar system, close to the sun where it was hot, only materials with high melting points could remain solid: rock and metal. That's why the inner planets, Mercury, Venus, Earth, and Mars, are rocky. In the outer solar system, beyond the frost line where water could freeze, the protoplanets could accumulate not just rock and metal, but also vast amounts of ice and gas. That's why the outer planets, Jupiter, Saturn, Uranus, and Neptune, are gas giants and ice giants, massive worlds with deep atmospheres. Earth formed in that inner region, a ball of molten rock in those early days, constantly bombarded by leftover planetesimals and comets. Its surface a sea of magma glowing red hot under a dark sky. The young sun was a fierce source of radiation, and the solar wind, a stream of charged particles flowing out from the sun, blew away any atmosphere Earth might have initially had. But Earth kept accumulating material, and as it grew, its gravity strengthened. Its interior remained molten from the heat of formation and from radioactive decay. And at some point in its early history, perhaps a few tens of millions of years after it formed, something dramatic happened. A Mars-sized protoplanet, sometimes called Theia, collided with Earth in a glancing blow. The impact was catastrophic. It vaporized rock, sent material splashing out into space, and released so much energy that both Earth and the impactor were partially melted. But out of that destruction came creation. The debris from the collision, a mix of material from Earth's mantle and from Theia, went into orbit around Earth and gradually coalesced to form the Moon. And that Moon has been orbiting Earth ever since, locked in a gravitational embrace, creating tides in Earth's oceans, stabilizing Earth's axial tilt, giving us regular cycles that have influenced the evolution of life. After the giant impact, Earth slowly cooled. Its surface solidified into a crust, though volcanic activity was far more intense than it is today. Water vapor in the atmosphere condensed and rained down, filling the low-lying areas to create the first oceans. Where that water came from is still debated. Some was probably trapped in the minerals of the rocks that built Earth. Some might have been delivered by comets, those icy visitors from the outer solar system. But however it arrived, water was essential for what came next. You can let your mind rest here for a moment, floating on the thought of those ancient oceans, dark and warm, covering a young planet still finding its equilibrium. The moon hangs large in the sky, much closer than it is now, moving away from Earth at a rate of a few centimeters per year, even today, pushed by tidal forces. The days are shorter, only about 6 hours long, because Earth is spinning faster. The sky might be a strange colour, perhaps orange or pink, because the atmosphere is different, rich in carbon dioxide and nitrogen and water vapour, but with no oxygen, not yet. And somewhere in those oceans, in some warm, shallow pool or deep-sea hydrothermal vent, or in the pores of volcanic rock, or in any number of environments that scientists debate about, chemistry becomes something more. Simple molecules, amino acids, and nucleotides begin to form. They're created by lightning strikes, by ultraviolet radiation from the sun, by chemical reactions in the presence of minerals and heat. These molecules accumulate, and some of them have the peculiar property of being able to catalyze reactions that create more of themselves. They're not alive, not yet, but they're autocatalytic, self-promoting. Over time, perhaps millions of years, these chemical systems become more complex. Molecules begin to group together, forming membranes that create boundaries between inside and outside. Primitive metabolisms develop, ways of extracting energy from the environment. Information storage emerges, first in simple chemical patterns, then in more sophisticated molecules like RNA. And at some point, these chemical systems cross a threshold that's hard to define but impossible to miss. They become alive. The first life on Earth was nothing like you. It was single-celled, microscopic, simple in structure, but sophisticated in chemistry. These cells could metabolize, extracting energy from their environment. They could reproduce, making copies of themselves. They could evolve, changing over generations through mutation and natural selection. And they were robust, capable of surviving in conditions that would be lethal to most modern organisms. For billions of years, life remained single-celled, but those cells were busy, evolving, diversifying, adapting to every niche and environment Earth had to offer. Some learned to harvest energy from chemicals like hydrogen sulfide or iron. Others, in one of the most important innovations in the history of life, learned to harvest energy from sunlight through photosynthesis. The earliest photosynthetic organisms didn't produce oxygen. They used different chemical pathways that released other substances. But eventually, about 2.5 billion years ago, a group of bacteria called cyanobacteria evolved oxygenic photosynthesis. The process that splits water molecules, uses the hydrogen to build organic compounds, and releases oxygen as a waste product. At first, this oxygen didn't accumulate in the atmosphere. It reacted with iron dissolved in the oceans, creating rust that precipitated out and settled to the bottom, forming the banded iron formations we can still see in ancient rocks today. But eventually, after hundreds of millions of years, the iron in the oceans was used up and oxygen began to build up in the atmosphere. This was the Great Oxidation Event, and it was catastrophic for many organisms. Oxygen is reactive, even toxic to life forms that evolved in its absence. There was probably a massive die-off. But for other organisms, oxygen represented an opportunity. It could be used as an electron acceptor in respiration, a process that releases far more energy than anaerobic metabolism. Life that could use oxygen had a huge advantage. The build-up of oxygen in the atmosphere also had other effects. It reacted with methane, a powerful greenhouse gas that had been keeping Earth warm, and its removal led to a series of glaciations, snowball Earth events, where ice covered most or all of the planet. But life survived, perhaps in refugia near the equator, or in the deep oceans, and when the ice melted, it bounced back. Let your eyes close now if they're not already closed. Feel the darkness behind your eyelids, the gentle weight of your eyelashes, the coolness of the air moving in and out of your nose. This darkness is not the absence of light, but a presence in itself, a restful place, like the deep ocean where life once sheltered, waiting for the world above to become habitable again. Around 1.8 billion years ago, another major innovation occurred. Some cells learned to live inside other cells in a mutually beneficial relationship called endosymbiosis. A larger cell engulfed a smaller one, probably a bacterium capable of aerobic respiration, but instead of digesting it, kept it alive inside. The smaller cell provided energy to the larger cell, and in return received protection and resources. Over generations, the smaller cell became so integrated that it could no longer live independently. It became an organelle, specifically a mitochondrion, the powerhouse of the cell, converting sugars and oxygen into ATP, the energy currency of life. Later, some cells engulfed photosynthetic bacteria, and those became chloroplasts, the organelles that perform photosynthesis in plants and algae. This process of endosymbiosis created eukaryotic cells, cells with nuclei and complex internal structures. All animals, all plants, all fungi, all protists, we're all eukaryotes, and we all carry within us the descendants of those ancient bacteria, working in every cell of our bodies right now, even as you rest. For another billion years, eukaryotic life remained mostly single-celled. But around 650 million years ago, something changed. Multicellularity evolved. not just once, but multiple times in different lineages. Cells began to stick together, to specialize, to cooperate. Some cells became dedicated to reproduction, others to digestion, others to sensation or movement. Bodies became possible, complex organisms made of millions or billions of cells working together. The Cambrian explosion, about 540 million years ago, saw a rapid diversification of body plans. Suddenly, the fossil record is full of animals with shells, with jointed legs, with eyes, with predators and prey engaged in evolutionary arms races. The oceans teemed with life, and it was becoming more complex, more diverse, more interconnected. Plants colonized the land about 470 million years ago, starting with simple mosses and liverworts that hugged the ground. They brought with them the cyanobacteria turned chloroplasts that allowed them to photosynthesize, and they began to transform the land, stabilizing soils, creating habitats, pumping oxygen into the atmosphere. Animals followed, first arthropods and eventually vertebrates, fish that evolved into amphibians that evolved into reptiles. The history of life on Earth is a long story of innovation and extinction, of radiations and die-offs. There have been 5 major mass extinctions that we know of, events where the majority of species went extinct in a geologically short period. The most famous is the one that killed the non-avian dinosaurs 66 million years ago, likely caused by an asteroid impact that threw up so much dust and debris that it blocked out the sun, causing a collapse in food chains. But there were others, some even more severe, like the Permian-Triassic extinction 252 million years ago, which wiped out over 90% of marine species. And yet life persists, it adapts, it fills in the gaps. After each extinction, survivors radiate into new forms, exploring the ecological space left vacant by the dead. The mammals, small and nocturnal during the age of dinosaurs, exploded in diversity after the dinosaurs went extinct, giving rise to everything from whales to bats to primates. Primates evolved around 55 million years ago, small tree-dwelling animals with grasping hands and forward-facing eyes. Over tens of millions of years, they diversified into all the groups we see today, monkeys and apes and prosimians. And one branch of the apes, the hominins, began to walk upright, to use tools, to develop larger brains. The genus Homo, our genus, appeared around 2.8 million years ago. There were many species of Homo, most of which are now extinct. Homo habilis, Homo erectus, Homo neanderthalensis, and around 300,000 years ago, in Africa, Homo sapiens, US, modern humans, evolved. We spread across Africa, and then in waves out into the rest of the world, reaching Europe and Asia, crossing land bridges and oceans to Australia and the Americas, adapting to every climate and ecosystem, from deserts to rainforest to Arctic tundra. And along the way, something remarkable happened. We developed language, symbolic thought, culture. We learned to make fire, to cook food, to create art, to tell stories. We looked up at the night sky and wondered what the stars were, where we came from, where we were going. We developed science, a method of asking questions and testing answers, of building models of reality that could make predictions. And we began to understand our place in the universe, to see the connections between the tiniest particles and the largest structures, to trace our lineage back through time to the first cells, to the first stars, to the Big Bang itself. You are the product of all that history, billions of years of cosmic and biological evolution. Every atom in your body has a story that stretches back to the beginning of the universe. The hydrogen in your water molecules was born in the Big Bang. The carbon in your organic molecules was forged in the core of a massive star. The gold in any jewelry you might wear, the iodine in your thyroid, the uranium in the rocks beneath your home. All of it was created in supernova explosions or neutron star collisions, violent cosmic events that seeded the universe with heavy elements. But let's zoom in now, from the cosmic scale to the human scale, from billions of years to the span of a single lifetime, to this moment, to you, lying here, breathing, thinking, feeling. Your body is an ecosystem, a collection of trillions of cells working in harmony. You have more bacterial cells in and on your body than human cells. Microbes that help you digest food, that synthesize vitamins, that train your immune system, that outcompete harmful pathogens. You are not a single organism, but a community, a walking, talking ecosystem. Your cells are constantly dying and being replaced. The cells lining your stomach last only a few days before they're shed and renewed. Red blood cells live for about 4 months. Skin cells last a few weeks. Even your bones are constantly being broken down and rebuilt by specialized cells. In a very real sense, you are not the same physical being you were a year ago. The matter has been replaced. What persists is the pattern, the information encoded in your DNA, the structure and function that define you, and your brain, that 3-pound lump of tissue in your skull, is the most complex structure we know of in the universe. It contains about 86 billion neurons, each connected to thousands of other neurons, forming a network of hundreds of trillions of synapses. Electrical signals race through this network at speeds up to hundreds of miles per hour. Chemical neurotransmitters diffuse across synaptic gaps, and somehow, from all this electrochemical activity, consciousness emerges. Thoughts, feelings, memories, dreams, the sense of self, the experience of being you, all of it arising from the coordinated activity of neurons and glia and blood vessels in your brain. We don't fully understand how consciousness works. It's one of the great unsolved mysteries of science. But we're learning. We know that different regions of the brain specialize in different functions. The occipital lobe processes vision. The temporal lobes handle hearing and memory. The frontal lobes are involved in planning, decision-making, personality. The limbic system generates emotions. The brainstem controls basic life functions like breathing and heart rate, working tirelessly right now, without any conscious effort from you, keeping you alive while you rest. Your brain is also constantly building models of reality, interpreting sensory data, predicting what will happen next. Vision, for example, is not a passive recording of the world, but an active construction. Light enters your eyes, strikes the retina, and is converted into electrical signals that travel down the optic nerve to the visual cortex. But what you see is not a direct representation of that data. It's an interpretation, a model built from expectations and memories and context. Your brain fills in gaps, smooths over inconsistencies, creates a coherent picture from incomplete information. The blind spot where your optic nerve passes through your retina. You don't see it because your brain fills it in. The way colours look different depending on surrounding colours. That's your brain interpreting context. Everything you perceive is mediated by your nervous system, shaped by evolution and experience. And right now, as you lie here listening to these words, your brain is processing them, decoding the sounds or the symbols if you're reading, extracting meaning, activating networks of associations, perhaps generating images or feelings or memories. Language is one of humanity's greatest inventions, a way of encoding thoughts into sequences of sounds or marks, transmitting them to another mind, where they are decoded back into thoughts. It's not perfect, not telepathy, but it's remarkable nonetheless, a bridge between consciousnesses, a way of sharing internal experiences. Take a moment to notice your breath again, the gentle rise and fall, the cool air entering, the warm air leaving. Breathing is automatic but also controllable. You can choose to hold your breath or to breathe faster or slower, but if you stop paying attention, the brainstem takes over and keeps you breathing without conscious thought. It's a beautiful example of how different levels of control operate in your nervous system, conscious and unconscious processes, working together seamlessly. The air you breathe in is mostly nitrogen, about 78%, with about 21% oxygen and trace amounts of other gases. That oxygen crosses from your lungs into your bloodstream, binds to hemoglobin molecules in red blood cells, and is carried to every cell in your body. Inside your cells, in the mitochondria, oxygen is used in cellular respiration, a process that breaks down glucose and generates ATP. Carbon dioxide, a waste product, is carried back to the lungs and exhaled. This gas exchange is happening right now, millions of times per second, in billions of cells, keeping you alive, keeping you warm. keeping your brain powered so you can think these thoughts. Your heart is beating, contracting, and relaxing, pushing blood through a circulatory system that, if laid out end to end, would stretch for about 60,000 miles in an adult, enough to circle the Earth more than twice. Blood flows from your heart through arteries, which branch into smaller arterioles, then into capillaries so narrow that red blood cells have to squeeze through single file. In the capillaries, oxygen and nutrients diffuse out into the tissues, and waste products diffuse back into the blood. Then the blood flows into venules, which merge into veins, which return the blood to your heart, and the cycle begins again. This system is a marvel of engineering, evolved over hundreds of millions of years. Fish have 2-chambered hearts. Amphibians and most reptiles have 3. Mammals and birds have 4, allowing complete separation of oxygenated and deoxygenated blood, which makes for a more efficient system and supports a higher metabolic rate. Your heart began beating when you were an embryo, just a few weeks after conception, and it will continue until the moment you die, beating about once per second, over 2 billion times in an average lifetime, never resting, always working. Let that beat become part of your awareness now. The steady rhythm in your chest, the pulse in your wrist or your neck if you pay attention. It's a drum that's been beating since before you were born, a rhythm as ancient as life itself. Single-celled organisms don't have hearts, but they have metabolisms, chemical reactions that cycle and pulse. Even the earliest cells had a kind of rhythm to their existence, oscillations in chemical concentrations, feedback loops that created temporal patterns. Your heartbeat is an echo of that ancient rhythm, scaled up, made complex, but fundamentally the same, the rhythm of life. Now let's think about temperature, the warmth you feel, or the coolness wherever you are. Temperature is molecular motion. Heat is the kinetic energy of particles jiggling around. The hotter something is, the faster its molecules are moving. When you touch something and it feels hot, molecules in that object are vibrating rapidly and transferring some of their kinetic energy to molecules in your skin, which your nerves detect and interpret as heat. Your body maintains a constant internal temperature around 98.6 degrees Fahrenheit or 37 degrees Celsius through a process called homeostasis. You generate heat through metabolism, through all those cellular processes that break down nutrients. When you're too hot, you sweat, and the evaporation of water from your skin cools you down. When you're too cold, you shiver, muscle contractions that generate heat. You constrict blood vessels near the skin to reduce heat loss, or dilate them to increase it. All of this is controlled automatically by your hypothalamus, a small region in your brain that acts as a thermostat. But temperature is also relative. What feels hot or cold depends on context, on what you're used to, on what you were just touching. A room at 70 degrees feels warm if you just came in from freezing weather, cool if you came from the summer heat. Your perception of temperature is not an absolute measurement, but a comparison, a signal about whether you're losing heat or gaining it, whether you need to adjust your behavior. And temperature affects everything. Chemical reactions go faster when it's hotter, slower when it's colder. That's why cold-blooded animals like reptiles are sluggish in cool weather, why your own metabolism increases slightly when you have a fever. It's why food spores faster in warm temperatures, why ice forms when water gets cold. Temperature is a fundamental parameter of reality, one that influences the structure and behavior of matter at every scale. Let's go smaller now, down to the molecular level, to the atoms that make up those molecules, to the subatomic particles that make up those atoms. An atom is mostly empty space. If an atom were the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be tiny specks orbiting somewhere in the outer seats. But that empty space isn't truly empty. It's filled with electric and magnetic fields, and at the quantum level with what's called the quantum foam, a seething sea of virtual particles that pop in and out of existence, borrowing energy from the vacuum for brief instants before annihilating. The nucleus of an atom is made of protons and neutrons, held together by the strong nuclear force, the strongest of the 4 fundamental forces, but one with a very short range. only effective over distances about the size of a nucleus. Protons are positively charged and they repel each other electromagnetically, so the strong force has to overcome that repulsion to hold the nucleus together. Neutrons, being uncharged, help by adding more strong force without adding more electromagnetic repulsion. Surrounding the nucleus are electrons, negatively charged particles that occupy probability clouds called orbitals. These are not orbits in the planetary sense, not little particles circling the nucleus. They're quantum states, regions where the electron has a high probability of being found if you measure it. And until you measure it, the electron doesn't really have a definite position. It exists in a superposition of all possible positions allowed by its orbital, collapsing into a specific position only when observed. This is one of the strange truths of quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales. At the quantum level, particles behave in ways that seem bizarre and counterintuitive compared to our everyday experience. They can exist in multiple states at once, in superposition until measured. They can be entangled with other particles so that measuring one instantly affects the other, no matter how far apart they are. They exhibit wave-particle duality, behaving like waves in some experiments and like particles in others. The famous double-slit experiment demonstrates this beautifully. If you fire electrons one at a time at a screen with two slits, they go through one slit or the other and hit a detector on the far side. But if you don't measure which slit they go through, they interfere with themselves, creating a pattern of light and dark bands on the detector, a wave interference pattern. Each electron seems to go through both slits at once, interfering with itself. But if you put a detector at the slits to see which one the electron goes through, the interference pattern disappears, and you get two bands, as if the electron chose one slit or the other. The act of measurement changes the outcome. This isn't a flaw in our equipment, or a sign that we're disturbing the system in some crude way. It's a fundamental feature of quantum reality. Particles exist in superpositions of states, and observation collapses the superposition into a definite outcome. What exactly constitutes an observation, what causes the collapse, is still debated. Some interpretations say it's the interaction with a macroscopic measuring device. Others say it's the involvement of consciousness, though that's controversial. Still others, like the many worlds interpretation, say there is no collapse at all, that the universe splits into multiple branches, one for each possible outcome, and we just experience the branch we're in. Quantum mechanics is the most precisely tested theory in all of science. Its predictions match experimental results to an astonishing degree of accuracy, and yet we still don't fully understand what it means, what it's telling us about the nature of reality. It works beautifully, but its implications are profound and unsettling. You can relax into that mystery now. The way the universe is stranger than you might have imagined, the way reality at its deepest level is probabilistic, fuzzy, indeterminate, until observed. There's something comforting about not knowing everything, about the universe still holding secrets, still inviting exploration and wonder. At the quantum level, even the vacuum of space is not empty. It's filled with quantum fields, one for each type of particle. The electromagnetic field pervades all of space, and photons are excitations of that field, little ripples in it. The electron field is everywhere, and electrons are excitations of it. The Higgs field gives particles mass through their interaction with it. Space is not a blank stage on which events occur, but an active participant, a dynamic tapestry of fields that interact and fluctuate. And these fields are subject to the uncertainty principle, which says that certain pairs of properties, like position and momentum, cannot both be known precisely at the same time. The more accurately you know one, the less accurately you can know the other. This isn't a limitation of measurement technology, but a fundamental feature of nature. It leads to phenomena like quantum tunneling, where particles can pass through barriers that classical physics says should be impenetrable, because there's a non-zero probability of finding them on the other side. Quantum tunneling is crucial for many processes. It's how the sun shines. In the core of the sun, protons have to get close enough to fuse, but they repel each other electromagnetically. At the eye temperatures and pressures in the sun's core, they don't have quite enough energy to overcome that repulsion classically. But quantum mechanically, there's a small probability that they can tunnel through the barrier, and given the sheer number of protons and the number of collisions happening every second, fusion occurs at a rate sufficient to power the sun for billions of years. Quantum effects also explain why atoms are stable. Classically, an electron orbiting a nucleus should radiate energy and spiral into the nucleus in a fraction of a second. But quantum mechanics forbids this. Electrons can only occupy certain discrete energy levels, and they can't drop below the lowest one, the ground state, so atoms don't collapse, and matter is stable, and you exist. Let's come back up in scale now, from the quantum to the everyday, to the world of objects and people and places. The coffee table in front of you, if there is one, feels solid, but it's mostly empty space. Atoms held together by electromagnetic forces, electrons repelling the electrons in your hand, creating the sensation of solidity. Matter resists being compressed because electrons resist being pushed too close together due to the Pauli exclusion principle, a quantum rule that says no two fermions, particles with half-integer spin like electrons, can occupy the same quantum state. The colours you see, if your eyes are open, or if you're imagining colours now, are electromagnetic radiation at different wavelengths. Red light has a longer wavelength, around 700 nanometers. Blue light has a shorter wavelength, around 450 nanometers. Your eyes have 3 types of cone cells, each sensitive to a different range of wavelengths, and your brain interprets the relative activation of these cones as colour. But colour is not an inherent property of light. It's a perceptual experience, a quale, something your brain creates in response to physical stimuli. Different animals see the world differently. Dogs have only 2 types of cones, so they see fewer colours, a more muted palette. Birds often have 4 types, allowing them to see into the ultraviolet. Mantis shrimp have 16 types, though it turns out they don't use them to see a wider range of colours, but to recognise colours more quickly. The world, as it truly is, independent of observers, is made of electromagnetic waves at various frequencies. Colour is how our brains interpret those waves, and it's different for different species, different for different individuals even, shaped by biology and experience. Sound is pressure waves in air, or another medium, molecules bunching up and spreading out in a pattern that propagates through space. Your eardrum vibrates in response to these pressure changes, and tiny bones in your middle ear, the malleus, incus, and stapes, the smallest bones in your body, transmit that vibration to the cochlea, a spiral structure in your inner ear filled with fluid. Inside the cochlea are hair cells, tiny sensory neurons with hair-like projections that bend in response to the fluid motion, opening ion channels, generating electrical signals that travel to your brain, where they are interpreted as sound. Different frequencies of sound are detected by hair cells at different positions along the cochlea, a kind of spatial encoding of frequency. High-frequency sounds activate hair cells near the base, low-frequency sounds near the apex. That's why hearing loss often affects certain frequency ranges more than others. Damage to hair cells in specific regions of the cochlea. And hair cells don't regenerate in mammals, so hearing loss from loud noise or aging is permanent. A reminder to protect your ears, to appreciate the sounds you can hear while you can hear them. The human range of hearing is roughly 20 to 20,000 Hz, cycles per second, though the upper limit decreases with age. Below that is infrasound, which we can sometimes feel as vibrations. Above it is ultrasound, which bats and dolphins use for echolocation, emitting high-frequency clicks and listening for the echoes, building a mental map of their surroundings from sound alone. Imagine being a bat, perceiving the world through sound, through the texture and timing of echoes, knowing the shape of a moth's wing by the way it reflects your clicks, navigating in total darkness with a richness of acoustic information we can barely comprehend. Every organism perceives the world through its own sensory apparatus, creating its own umwelt, its own perceptual world, shaped by evolution to detect what's relevant for survival and reproduction. You live in a human umwelt, detecting a narrow slice of the electromagnetic spectrum as light, a limited range of pressure waves as sound, certain chemicals as smells and tastes, temperature and pressure through your skin. But beyond your senses, there are phenomena you can't directly perceive. Radio waves, microwaves, X-rays, gamma rays, all forms of electromagnetic radiation outside the visible spectrum. Magnetic fields, which some animals can sense and use for navigation, but which you experience only through their effects on other objects. Gravitational waves, ripples in space-time, caused by accelerating massive objects, passing through you right now from colliding black holes billions of light years away, stretching and squeezing space by amounts far too small for you to notice. Science gives us tools to extend our senses, to detect and measure phenomena beyond our natural perceptual range. Telescopes gather light from distant stars, amplifying faint signals. Radio telescopes detect long wavelength radiation, revealing pulsars and quasars and the cosmic microwave background. X-ray telescopes, which have to be in space because Earth's atmosphere absorbs X-rays, show us hot gas in galaxy clusters and accretion disks around black holes. Gravitational wave detectors like LIGO use lasers and mirrors to measure changes in distance smaller than the width of a proton, detecting the mergers of black holes and neutron stars. Each new instrument, each new way of looking, reveals a universe more complex and more beautiful than we imagined. The night sky looks one way to your naked eye, a scattering of stars, the band of the Milky Way if you're far from city lights. Through binoculars, you can resolve the moons of Jupiter, the rings of Saturn, the Andromeda Galaxy as a fuzzy patch. Through a telescope, nebulae bloom into colourful clouds, star clusters resolve into thousands of individual points, galaxies show their spiral structure, and with space telescopes like Hubble and James Webb, we see back in time, looking at light that has been travelling for billions of years, seeing galaxies as they were when the universe was young. That's one of the strange things about astronomy. Because light takes time to travel, looking at distant objects is looking into the past. The sun is about 8 light minutes away, so when you see the sun, you're seeing it as it was 8 minutes ago. The nearest star, Proxima Centauri, is about 4 light years away, so you see it as it was 4 years ago. The Andromeda Galaxy is 2.5 million light years away, so the light you see from it left when human ancestors were just beginning to use stone tools. The farthest galaxies we can see are over 13 billion light years away, and we see them as they were just a few 100 million years after the Big Bang. Young galaxies still forming their first stars. There's a horizon to what we can see, the cosmic light horizon, determined by the age of the universe and the speed of light. Beyond a certain distance, light hasn't had time to reach us yet. And because the universe is expanding, that horizon is always moving, new regions of space coming into view. But there are also regions moving away from us faster than light. Not because they're moving through space faster than light, which is forbidden, but because space itself is expanding, carrying them away. We will never be able to see those regions. They are beyond our cosmic horizon, forever inaccessible. The expansion of the universe is one of the most important discoveries of modern cosmology. In the 1920s, Edwin Hubble measured the distances to galaxies using variable stars called Cepheids, whose brightness oscillates in a regular way that's related to their intrinsic luminosity. By comparing their apparent brightness to their intrinsic brightness, he could calculate how far away they were, and he found that the farther away a galaxy was, the more its light was red-shifted, shifted toward longer wavelengths. This redshift is due to the Doppler effect, the same effect that makes a siren sound higher pitched as it approaches and lower pitched as it moves away. For light, motion toward us shifts it to the blue, motion away shifts it to the red, and Hubble found that nearly all galaxies are red-shifted, meaning they're moving away from us, and the farther away they are, the faster they're receding. This is Hubble's law, and it implies that the universe is expanding, that space itself is stretching, carrying galaxies along with it. If the universe is expanding now, it was smaller in the past, denser, hotter. Extrapolate back far enough, and you reach the Big Bang, the beginning of space and time as we know it. This expansion is not an explosion into pre-existing space, but an expansion of space itself. There is no center to the expansion, no edge. Every point in space is moving away from every other point, like dots on the surface of an inflating balloon, and the expansion is accelerating. In the late 1990s, astronomers studying distant supernovae found that the expansion rate is increasing over time, which was a huge surprise. Something is pushing space apart, counteracting the attractive force of gravity. We call this dark energy, and it makes up about 68% of the total energy content of the universe. We don't know what it is. It might be a cosmological constant, a property of space itself, an energy density inherent in the vacuum. Or it might be some kind of dynamic field, something that changes over time. We're not sure, and it's one of the biggest mysteries in physics. Dark matter and dark energy together make up about 95% of the universe. Ordinary matter, the stuff that makes up stars and planets and you, is only about 5%. We live in a universe dominated by things we don't understand, which is both humbling and exciting. There's so much left to learn. Let your mind drift now with that thought. The vastness of what we don't know, the frontier of knowledge always receding, always inviting us forward. Science is not a collection of facts, but a process, a way of asking questions, making observations, formulating hypotheses, testing them, revising our understanding. It's iterative, self-correcting, always provisional. Scientific knowledge is the best understanding we have at the moment, based on the evidence available, but it's always subject to revision if new evidence comes along. And that's a strength, not a weakness. Science doesn't claim absolute certainty. It builds models that match observations, that make predictions, that are useful for understanding and manipulating the world. And when a model fails, when observations don't match predictions, we revise the model or replace it with a better one. That's how we progress, how we learn. Think about the journey from geocentrism to heliocentrism to our modern understanding of the cosmos. For centuries, people believed Earth was the center of the universe, with the sun and planets and stars revolving around it. It made intuitive sense. The ground feels stationary, and the sky appears to move. Ptolemy developed an elaborate system of epicycles to explain the observed motions of the planets within a geocentric framework. It was complex, but it worked reasonably well for prediction. Then Copernicus proposed that the sun was at the center, and Earth and the other planets orbited it. This was simpler in some ways, but it was controversial, partly because it conflicted with religious doctrine, and partly because it didn't immediately give better predictions than the Ptolemaic system. But Kepler refined it, discovering that orbits are ellipses, not circles, and formulating his 3 laws of planetary motion. Galileo observed the moons of Jupiter, demonstrating that not everything orbited Earth, and saw the phases of Venus, which made sense in a heliocentric model, but not in a geocentric one. Newton provided a physical explanation for Kepler's laws with his law of universal gravitation, showing that the same force that makes apples fall also keeps planets in orbit. And then Einstein refined our understanding further with general relativity, showing that gravity is not a force, but the curvature of spacetime caused by mass and energy. Each step was a refinement, a deeper understanding, revealing that our previous models were approximations, useful but incomplete. And even now, general relativity and quantum mechanics, our 2 most successful theories, are incompatible with each other. General relativity describes gravity and the large-scale structure of spacetime. Quantum mechanics describes the behavior of particles and forces at the smallest scales. Both are incredibly accurate within their domains, but they can't both be exactly right, because they give different answers in extreme situations, like the singularity at the center of a black hole, or the moment of the Big Bang. We need a theory of quantum gravity, a unified framework that incorporates both, and physicists are working on it, exploring ideas like string theory and loop quantum gravity and others. We don't have the answer yet, but we're searching, probing the boundaries of knowledge. There's a beauty in this, in the openness, in the acknowledgement of what we don't know. Science is not dogma. It's exploration, a conversation between our models and the universe, with the universe always having the last word. And that process of exploration is deeply human, driven by curiosity, by the desire to understand, by the joy of discovery. Humans have always looked at the night sky and wondered. Ancient cultures saw patterns in the stars, constellations, and wove stories around them. The Greeks imagined gods and heroes. The Chinese saw celestial bureaucracy. Indigenous Australians have stories of the emu in the sky, seen not in the stars, but in the dark nebulae of the Milky Way. Every culture has tried to make sense of the cosmos in its own way, and modern science is a continuation of that tradition, using systematic observation and mathematical models instead of myth, but driven by the same fundamental curiosity. And we've come so far. We've walked on the moon. We've sent robots to explore Mars, to land on comets, to fly by Pluto. We've built a space station where humans live and work in orbit. We've launched telescopes that peer deep into space and time. We've split the atom and built particle accelerators to probe the smallest scales of reality. We've sequenced the human genome and begun to understand the molecular basis of life. We've developed technologies that would seem like magic to our ancestors: computers, the internet, smartphones, artificial intelligence. But we've also created problems. Climate change, driven by the burning of fossil fuels, is altering the planet's climate faster than ecosystems can adapt. Biodiversity is declining, species going extinct at rates not seen since the last mass extinction. Pollution contaminates air and water and soil. Nuclear weapons threaten our survival. Inequality, conflict, and suffering persist. The same intelligence that allows us to understand the universe also gives us the power to harm ourselves and our planet. Yet there's reason for hope. Humans are also capable of cooperation, compassion, creativity. We're developing renewable energy technologies, solar and wind and batteries, that can replace fossil fuels. We're learning to manage resources more sustainably. We're communicating across cultures, sharing knowledge, working together on global challenges. The same scientific method that revealed the problems can help us solve them if we choose to apply it, if we choose to act on what we know. You, lying here, are part of that larger story, a human living at this particular moment in history, shaped by the past, shaping the future. Your choices matter, small as they might seem. The energy you consume, the food you eat, the way you treat others, the stories you tell, the values you embody, all of it ripples out, influences the world in ways you might never see, but that are real nonetheless. And you're connected to everything else, not just in some vague metaphorical sense, but in concrete physical ways. The atoms in your body were once part of other things, will be part of other things again. The water you drink has cycled through oceans and clouds and rivers and countless organisms over billions of years. The oxygen you breathe was exhaled by plants and phytoplankton. The food you eat was grown in soil enriched by decomposing matter, by fungi and bacteria breaking down the dead and making nutrients available to the living. You are a node in a vast web of relationships, ecological and chemical and physical, connected to the whole Earth system, to the biosphere, to the carbon cycle, and the water cycle, and the nitrogen cycle. Even your consciousness, as subjective and personal as it feels, is not separate from the physical universe. It arises from the activity of your brain, from neurons and neurotransmitters, from patterns of electrical and chemical signals. And your brain is made of atoms that obey the laws of physics, atoms that were forged in stars, atoms that are subject to quantum effects and thermodynamics and electromagnetism. There is no dualism, no ghost in the machine. You are entirely natural, entirely physical, and yet you are also conscious, aware, experiencing. Matter can be aware of itself. The universe can look at itself through your eyes, think about itself through your brain. That's profound. Let's think about time now. The way it flows, the way the present moment is always slipping into the past, the future always becoming the present. Time is strange. We experience it as a flow, a river carrying us from birth toward death, from past through present toward future. But physics treats time as a dimension, similar to the 3 dimensions of space, a coordinate that specifies when an event occurs, not something that flows. In relativity, space and time are united into space-time, a 4-dimensional fabric. Events are points in space-time, and the history of a particle or a person is a world line, a curve through space-time, and time is relative. It passes at different rates for observers moving at different speeds or in different gravitational fields. A clock on a fast-moving spaceship runs slower than a clock on Earth. From Earth's perspective, a clock deep in a gravitational well near a massive object runs slower than a clock far from any mass. Time dilation is a real measured effect. Astronauts on the International Space Station age slightly slower than people on Earth's surface. GPS satellites have to account for both the slower time due to their speed and the faster time due to being farther from Earth's gravity, or their clocks would drift out of sync and the system would give inaccurate positions. The speed of light is constant in all reference frames, which leads to all these strange effects. Nothing with mass can reach the speed of light, because as you go faster, your mass effectively increases and it takes more and more energy to accelerate further, approaching infinite energy as you approach the speed of light. But light itself, photons, always travel at light speed, and from their perspective, no time passes at all. A photon emitted from a distant galaxy billions of years ago, from its own perspective, arrives at your eye instantly. It experiences no duration between emission and absorption. Time, for a photon, does not exist. And then there's the arrow of time, the fact that time seems to have a direction. We remember the past, not the future. Eggs break, but don't spontaneously reassemble. Heat flows from hot to cold, not the reverse. Entropy, a measure of disorder, increases over time, according to the second law of thermodynamics. That's the arrow of time, the asymmetry between past and future. But at the fundamental level, the laws of physics are time-symmetric. If you filmed subatomic particles interacting and played the film backward, it would still look like valid physics. The asymmetry, the arrow, of time emerges at the macroscopic scale from the statistical behavior of large numbers of particles. The universe started in a very low entropy state, highly ordered, and it's been evolving toward higher entropy, more disordered ever since. That evolution, that increase in entropy, gives us the arrow of time, the direction from past to future. Eventually, if current models are correct, the universe will reach maximum entropy, a state called heat death, where all energy is evenly distributed, where no more work can be done, where stars have burned out and black holes have evaporated, and the temperature everywhere is just barely above absolute zero. But that's trillions upon trillions of years in the future, so far away that it's almost meaningless. For now, the universe is vibrant, full of structure and energy and life. And you're here, in the middle of it all, a temporary arrangement of matter and energy, complex and conscious, experiencing this moment. Your existence is unlikely, contingent on countless historical accidents, and yet here you are. The universe has conspired through billions of years of evolution to create you, to give rise to a being capable of looking back and understanding, at least partially, the story of how you came to be. There's something poetic about that, something that transcends the mere facts. We are stardust contemplating stars, matter pondering matter, the universe aware of itself. And in that awareness, there's meaning, even if it's meaning we create ourselves. Meaning that's subjective and personal and not written into the laws of physics. You get to decide what matters to you, what you care about, how you want to spend the brief time you have. And right now, you're spending it here, in this quiet moment, resting, listening, letting your thoughts wander through space and time, through science and philosophy, through the very big and the very small. This is a gift you're giving yourself. This pause, this stillness, this opportunity to reflect and wonder. Your breathing has probably slowed by now, deepened. Your muscles have relaxed, releasing tension you might not have even known you were holding. Your heart rate has settled into a calm, steady rhythm. Your mind might be drifting, thoughts becoming less linear, more dreamlike, as you approach the threshold of sleep. Sleep is another mystery, something we do every day but don't fully understand. We know it's essential. Deprived of sleep, cognitive function declines, mood suffers, the immune system weakens, and eventually, prolonged sleep deprivation can be fatal. During sleep, the brain is far from inactive. It cycles through different stages, from light sleep to deep sleep to REM sleep, where most dreaming occurs. In deep sleep, the brain clears out metabolic waste products through the glymphatic system, a kind of cleaning cycle that's much more active when you're asleep. In REM sleep, the brain is almost as active as when you're awake, processing memories, consolidating learning, perhaps working through emotional experiences. Dreams are strange, surreal narratives that often don't make logical sense, but feel meaningful in the moment. The prefrontal cortex, the part of the brain involved in logic and critical thinking, is less active during dreams, which might be why dream logic is so bizarre. But the emotional centers are active, which is why dreams can feel so intense, why you can wake from a dream with your heart pounding or tears on your face. What are dreams for? That's still debated. They might be a way of processing emotions, integrating new experiences with old memories, rehearsing responses to threats, or simply a byproduct of neural activity during sleep. Maybe they serve multiple functions. Maybe they're meaningful, or maybe they're just noise, the brain's way of keeping itself occupied while the body rests. But they're part of the human experience, part of the richness of consciousness, and they've inspired art and literature and philosophy for as long as humans have been telling stories. Tonight, you might dream. You might revisit places you've been, people you've known. You might find yourself in impossible situations, flying or falling or unable to move. You might solve problems, have insights, see connections you didn't see while awake. Or you might not remember your dreams at all, waking with only a vague sense of having been somewhere else. And when you wake, the world will be here, the same physical universe governed by the same laws. But you'll see it through new eyes, refreshed, restored, ready to engage again. The sun will rise, if it's daytime where you are, a reminder of the steady fusion reactions in its core, the conversion of hydrogen to helium, the release of energy that has travelled 93 million miles through space to warm your skin and power the biosphere. The moon might be visible, a reminder of the giant impact that formed it, of the tidal forces that slow Earth's rotation and push the moon gradually farther away. The stars will wheel overhead, as they have for billions of years, each one a sun, many with planets of their own, some perhaps harbouring life, other consciousnesses looking up at their own skies, wondering if they're alone. We don't know if we're alone in the universe. The universe is vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars, and we've detected thousands of planets orbiting other stars, many in the habitable zone where liquid water could exist on the surface. The chemical building blocks of life, amino acids and other organic molecules, are found in meteorites and in the clouds of gas and dust between stars. Life arose on Earth relatively quickly after the planet cooled enough to support it, which suggests that maybe it's not that hard for life to start, given the right conditions. But we haven't found any evidence of extraterrestrial life yet. We've searched, listening with radio telescopes for signals from other civilizations, examining the spectra of exoplanet atmospheres for biosignatures like oxygen and methane, sending rovers to Mars to look for signs of past or present life. So far, nothing. The Fermi paradox asks, if life is common, where is everybody? Why haven't we seen any signs of other civilizations? No megastructures, no radio signals, no probes visiting our solar system. There are many possible answers. Maybe life is common but intelligent. Technological life is rare. Maybe civilizations tend to destroy themselves before they become spacefaring. Maybe space is just too vast, the distances between stars too great for travel or even communication to be practical. Maybe we're looking in the wrong places or in the wrong ways, or maybe we're genuinely alone, the only consciousness in the universe, at least in our part of it. That would be lonely but also special, a responsibility even to preserve and cherish the life we have, because it might be the only life there is. Or maybe the universe is teeming with life, and we just haven't found it yet. Maybe in our lifetime, will detect a signal, see a sign, make contact. That would be one of the most profound moments in human history, a realization that we're not alone, that consciousness has arisen elsewhere, that the universe is not silent and empty but vibrant and inhabited. For now, we have each other, 7.9 billion humans sharing this planet, along with millions of other species, all of us descendants of that first life that arose billions of years ago, all of us related, all part of the same family tree. We share a common genetic code, a common biochemistry, a common origin, and we share this moment in time, this thin slice of history, this brief window between the past and the future. You're part of a species that has achieved remarkable things, that has created art and music and literature, that has explored the planet and begun to explore space, that has unravelled many of the mysteries of nature and continues to push the boundaries of knowledge. But you're also part of a species that has caused great harm, that has waged wars, enslaved people, destroyed ecosystems. We're capable of both great beauty and great ugliness, and the future is not predetermined. It will be shaped by choices, billions of choices made by billions of people, including you. What kind of future do you want? What kind of world do you want to leave for those who come after? These are not idle questions. They're urgent, pressing, calling for thought and action. But not right now. Right now, you're resting, letting go, drifting. Feel the softness around you, the support beneath you. Notice the sounds, near and far, the hum of the world going about its business. Notice the temperature, the air on your skin. Notice the darkness or the light, depending on your environment. Let it all be, without needing to change anything, without needing to do anything. You are enough, just as you are. You don't need to be more productive, more successful, more anything. In this moment, simply existing is enough. You are a part of the universe experiencing itself, and that is beautiful and sufficient. The cosmos does not judge you. The stars do not care if you made mistakes today, if you didn't accomplish everything on your to-do list. Gravity holds you regardless. Light reaches you regardless. The laws of physics apply to you just as they apply to everything else. Impartially, consistently, without favour or disdain. There's a kind of comfort in that, in the impersonality of nature, in the fact that the universe is what it is, indifferent to our worries and fears, and yet, within that indifferent universe, there are pockets of care, of meaning, of connection. You care about people, and people care about you. You find things beautiful, meaningful, worth pursuing. That's not written into the physics, but it's real nonetheless. As real as anything else, because it's part of your experience, part of what it means to be human. Consciousness is an emergent property, arising from the complex interactions of simpler components, neurons firing in patterns, but it's not reducible to those components. You can't understand a symphony by analysing each note in isolation. You can't understand a painting by cataloguing the molecules of pigment. You can't understand consciousness by merely listing the neurons. There are levels of organisation, levels of description, and each level has its own validity, its own reality. At the level of atoms, you're a collection of particles held together by electromagnetic forces. At the level of cells, you're a community of trillions of living units cooperating. At the level of organs, you're a system of specialized structures working together. At the level of the whole organism, you're a person, an individual with thoughts and feelings and intentions. All of these descriptions are true, simultaneously, each appropriate for different questions, different contexts. And you're also part of larger systems, social, ecological, cosmic. You're embedded in a web of relationships, influencing and influenced by others, by culture, by history, by the environment. You're not a separate, isolated entity, but a node in a network, a process rather than a thing, constantly changing, constantly in flux. The atoms that make you up will be part of other things someday. The carbon in your body might end up in a tree, in the soil, in the ocean, in another organism. The cycle continues. Matter and energy flow through you, and you are a temporary pattern, a beautiful, complex, conscious pattern, but temporary nonetheless. That might sound sad, but it can also be liberating. If you're temporary, then so are your problems, your worries, your embarrassments. They will pass. Everything passes. The only constant is change. The only permanence is impermanence. Buddhists have been saying this for millennia, and physics agrees. Entropy increases, systems evolve, nothing stays the same, so savor the moments that matter. Notice the beauty around you, feel the love, the connection, the wonder, because these moments are precious, not despite their transience, but because of it. A sunset is beautiful, partly because it doesn't last. A piece of music moves you because it unfolds in time and then ends. Life is meaningful, partly because it's finite, because every moment is unique and irreplaceable. You're here now, and that's a gift. The universe is vast and old and mostly empty, and yet here you are, alive, aware, able to contemplate it all. You won the cosmic lottery just by existing. The odds against any particular person existing are astronomical, depending on countless chance events. The right sperm meeting the right egg, your parents meeting, their parents meeting, going back through generations, through millions of years of evolutionary history, through the formation of Earth, through the lives and deaths of stars. Change any one of those events, and you wouldn't be here. But you are. Against all odds, you exist. And you exist at a time when we understand so much about the universe, when we can look back at the Big Bang, trace the evolution of galaxies, understand the chemistry of life, peer into the quantum realm. You have access to more knowledge than any human in history, more than emperors or scholars of past ages could have dreamed of. The sum of human understanding is at your fingertips, a few clicks away. But knowledge alone is not enough. Wisdom is knowing what to do with knowledge, how to apply it, how to live well. And wisdom comes from experience, from reflection, from making mistakes and learning from them, from listening to others, from being present in your own life. Right now, you're being present. You're here, in this moment, listening, breathing, feeling. This is a practice, this presence, this awareness. It's something you can cultivate, something that gets easier with repetition. And it's valuable, perhaps more valuable than any external achievement, because it's the ground of your experience, the foundation of your life. Your life is made of moments, strung together like beads on a thread. Some are dramatic, memorable, life-changing. Most are ordinary, quiet, easily forgotten. But they're all you have. The past is gone, exists only in memory and in its effects on the present. The future hasn't happened yet, exists only in anticipation and planning. The present is the only moment that's real, that you're actually experiencing. And it's always now. It's always this moment, this breath, this sensation. So rest in this moment, let it hold you. Let the universe support you, gravity cradle in your body, the air fill in your lungs, the ground beneath you solid and reliable. You don't have to do anything, achieve anything, prove anything. You can just be, just exist, just experience. And as you rest, know that you're part of something larger, something ancient and ongoing. The atoms in your body have been recycled countless times, through stars and supernova, through oceans and atmospheres, through countless organisms. You carry within you the history of the universe. You are a way for the cosmos to know itself, and that is a profound and beautiful thing. Let that thought settle over you like a soft blanket, comforting and warm. You are stardust, arranged in a pattern that can think and feel and wonder. You are the universe experiencing itself, locally, briefly, uniquely. And that is enough. That is more than enough. That is everything. Your eyelids are heavy now, if they're not already closed. Your body is relaxed, sinking deeper into rest with each breath. Your thoughts are slowing, becoming less distinct, more dreamlike. The boundary between waking and sleeping is soft, permeable, and you're drifting across it, gently, easily, naturally. There's no effort required. Sleep will come when it comes, and if it doesn't right away, that's okay too. Lying here, resting, letting your body recover, that's valuable in itself. You don't have to force anything, you can just allow, just be open to whatever happens next. The universe is unfolding exactly as it should, moment by moment, according to the laws of physics, the principles of thermodynamics, the dynamics of complex systems. You're part of that unfolding, not separate from it. Your thoughts, your feelings, your dreams, they're all natural phenomena, as much a part of the universe as stars and galaxies and black holes. And the universe is not a cold mechanical place devoid of meaning. It's a place where matter can become complex enough to experience, to be aware, to care. It's a place where beauty exists, where love is possible, where consciousness can emerge and contemplate its own existence. That's not separate from the physics. That's what the physics enables, what it makes possible. You are a miracle, not in the sense of violating natural law, but in the sense of being an extraordinary, unlikely, wonderful one outcome of natural processes. The same process that formed galaxies and stars formed you, and you are no less cosmic, no less connected to the whole than any celestial object. So rest easy, knowing you belong here, that you're exactly where you're supposed to be, that the universe has made a place for you, however briefly. You are held by forces older than time, part of a story that began billions of years ago and will continue long after you're gone. But right now, in this moment, you are here, and that is a privilege, a joy, a gift. Let yourself drift now, let go of the day, let go of your thoughts, let go of everything that's holding you to wakefulness. Sink into the softness, into the warmth, into the quiet. Let the darkness embrace you, gentle and safe, like the darkness between stars, like the darkness before the universe was born, like the darkness of the womb, the first place you ever knew. You are safe, you are whole, you are enough, and as you slip into sleep, may you rest deeply, may you dream sweetly, may you wake refreshed and ready to meet the world again, to continue your journey through this strange and beautiful universe, this cosmos that is your home, your origin, your destiny, and in a very real sense, yourself. Sleep well, traveller. The stars are watching over you as they always have, as they always will, shining their ancient light across the void, connecting you to everything that is, everything that was, everything that will ever be. You are not alone. You are part of the whole, and the whole is part of you. Rest now, and let the cosmos carry you gently into dreams, into the soft embrace of sleep, into the quiet heart of the universe, where all things rest, where all things return, where all things are held in the infinite tenderness of existence itself. Good night.